calculating the rates of reactions for various rate laws, given reaction data at multiple points. And let's see what we can do with that, what information we can get about what's going on. Okay, so the method 2, the method 1 was the method of initial rates. That you just were collecting data from the initial time point with different experiments. At this point, we only have one experiment that we're carrying out, and we analyze what is going on. It's best for simple cases with a single reactant. If there's multiple reactants, then you got to deal with, it's not this simple. You have to fit to other curves. But in the case that it is a unimolecular reaction, that the rate is equal to K times the concentration of your single reactant to some power, this can illustrate what those rates are. So first of all, you assume that a certain order, you have to try a couple different cases, 0, first, second, it's probably one of those for the single reactant, and use the corresponding integrated form of the assumed rate law. And you plot a graph of rate data, and we'll go over what rate data is versus time in the form of the integrated rate equation. And if a straight line results, you get the correct guess for n. And if you have that, then you can look at the slope and get the information about the rate, figure out the initial concentration, and so forth. So let's dive in and look at examples of this. So we have some case where we've got a decomposition reaction to produce methane and carbon monoxide, and I'm measuring my concentration of the reactant. Again, this is for a single experiment now. We don't have to do initial rates. We have a single experiment, and we look to see how much is left as a function of time. And so let's assume that it's a zeroth order reaction, right? That's the simplest thing. So what we do is we identify what data here we need to plot so that's linear. So this would be the concentration of A is what you're going to get a linear function for. If you plot A versus C for a zeroth order reaction, you get a straight line. If it's not a zeroth order reaction, you're not going to get a straight line. And frankly, that doesn't look very much like a straight line. I mean, maybe if the data is super noisy, but our conclusion would be that's probably not a zeroth order reaction. Okay, so we give up on that. So we take the same data, and then we look at the integrated rate law for a first order reaction. And there we know that log of concentration of A times is equal to minus KT plus log of A0. So in that case, we want to be plotting log of A versus time. So we have the time in minutes and the log of A there. And you can see, that's still not really a straight line unless we were really bad at data management. So let's assume that we were keeping good data. Let's try the other option. Let's try plotting now 1 over A versus time. So we know in that case, for a second order reaction, 1 over A is equal to KT plus 1 over A0. If we plot 1 over A versus temperature, then we should indeed get a straight line. And this looks much more like a straight line. This looks like fakes data. It probably is. I think I just made up this data, did it a couple years ago. I think I just made up the data to make it fit. So yeah, this is very, very clean data. And it's a straight line. So our assumption would be this data is probably coming from a second order reaction. It makes sense. You got a gas that's reacting. Sure, could be a second order reaction. So how do we determine the rate? Well, let me go back for a second. So if we're plotting in a straight line, then we know that the slope is equal to K. So we can just read off what the slope of the line was, and we can just, for example, calculate the slope with a rise versus run, right? The slope is just the rise over the run. If you want to be fancy, you can use some computer program to fit all the data to a line and extract a least mean squares. Yeah, you'll cover that more in a data analysis class. So for now, we'll keep it simple. We'll just look at the slopes. So rise over run, x2 minus x1. So this minus this divided by the time over there. Well, that's 0.499. Or we could look at these two times, this time and this time. Sorry, the concentration, 1 over the concentration of this time, 1 over the concentration of this time. And these two time periods, we get that. So we've got several different things we can compare to. And what we see, the slope's about the same. So the slope is about 0.50. Yeah, if you're doing, in a data analysis class, we could, calculate an estimated uncertainty, but, it's pretty clear that the answer is 0.50 plus or minus a little bit. So we'll go with that. Up to significant digits, it's 0.50. Great. Linear, second order, 0.50. One question. 0.50 watts, right? So tell me, it's 0.50 in what units? So pause the video, think about it, and let me know your let me know your answer. Of course, you're not going to let me know your answer. You can email me and let me know if you answer if you want, but come up with your answer and see if it's one of these answers here and if you're confident in that. So pause and think about it. All right, we're back. What are the units? Well, there's a couple ways to do it. You could just remember, oh, what are the units for a second order reaction, right? Second order rate law, right? That's one way to do it. But if we don't remember that, can we work this out from the data we have? Well, yeah, because we have this equation that has to have equality. We know that, concentration is in molar. So 1 over molar here, 1 over molarity is equal to kT plus 1 over molarity. So for this to be equal, kT has to have units of 1 over mole. And so T has units of time. So K is going to have units of 1 over mole times seconds. So the units will be mole minus 1, second minus 1. So those are the units. Right? We could have done this by just remembering what a second order reaction units would be, or just look at the math. What is the math that makes this consistent? KT has to have units of 1 over molarity. So therefore, K has to have units of inverse molarity times inverse seconds.